So in this video, let's see Dirac's matrices. So from the Dirac relativistic equation, we have got some relations: alpha x square equals alpha y square equals alpha z square equals beta square equals I, like that. So alpha x, alpha y, alpha z and beta, all of them are nothing but Dirac's matrices. So we are going to now derive these Dirac's matrices. So that is this video about. So here is the theoretical part. So Dirac's matrices, that means matrices for alpha and beta. The squares of all the four matrices are unity, so that their eigenvalues are +1 or -1. So as we have seen in Dirac's relativistic equation, alpha x square, alpha y square, alpha z square, beta square, all of them are all equal to I, that is a unit matrix. So that is the thing they are mentioning. So the squares of this matrix is however unity, so that their eigenvalues are 1 or -1, they are saying. How they are saying this is because if lambda is the eigenvalue of a matrix, let us suppose. So if lambda is the eigenvalue of a given matrix, then lambda square is the eigenvalue of square of that matrix. So here what they are mentioning is, so that their eigenvalues are +1 and -1. The squares of this matrix is unity. That means lambda square is equals to 1. Then so that their eigenvalues are +1 or -1. So how this is possible means, if we take lambda is equals to 1 square, then we would have 1. And if we take lambda is equals to -1, then also we would have -1 whole square, that is 1. So hence they are mentioning the eigenvalues of these matrices are +1 or -1. So that is the thing here. So let us arbitrarily choose beta as the matrix that is to be diagonal, and we rearrange its rows and columns. So rearrange its rows and columns so that all the +1 eigenvalues are grouped together in a matrix of rank n, and all the -1 eigenvalues are grouped together in a matrix of rank m. So as we have discussed, +1 as well as -1 are the eigenvalues of these matrices. So we are arbitrarily choosing beta as the diagonal matrix. So this is nothing but diagonal. Only principal diagonal elements would be present, and remaining all the elements would be 0. So we are choosing this beta matrix as the diagonal matrix. And also it is mentioned here that +1 eigenvalues are grouped together in a matrix of rank n. So here +1, all the +1 eigenvalues grouped together, and all the -1 eigenvalues grouped together, and their rank in a matrix of rank n, and another thing in the matrix of rank m. So rank nothing but number of independent rows or columns a matrix can have. So here this is 2 independent rows. So 2 matrix of rank 2, and this is also matrix of rank 2, like that. Separately if we consider 1 1. So 2 rows, 2 independent rows, and here again 2 independent rows. So here 2 rows, and here also 2, that means it is a matrix of rank 2, like that. So that one they are saying. So here it is mentioned, so the matrix beta can be expressed as, so beta could be expressed in this form 1 0 or 0 -1, or else this form. So abbreviation, so if we consider I 0 0 minus I here, so that could be written as, in the place of I, 1 0 0 1, and here 0 0, 0 is nothing but null matrix, and here minus I, -1 0 1, -1 0 0 -1, like that. So this is the, if we suppose, so beta matrix would be of this form. We are just taking the matrix considering the matrix to be of this form, because here if we see its eigenvalues are 1, and as well as -1. So y means if we do a minus lambda I or beta minus lambda I like that, if we substitute in that formula, you would have 1 minus lambda, 1 minus lambda, minus 1 minus lambda, minus 1 minus lambda like that. So that lambda is nothing but 1 and -1 like that we used to get. So like that eigenvalues. So next, all the four matrices alpha x, alpha y, alpha z and beta are such that their squares are unity. So this one we have already discussed. We have been discussing this point from the beginning of the session, and they anti-commute with one another in pairs. So we are also have found another anti-commutation relations in the previous Dirac's relativistic equation. So that is alpha x beta plus beta alpha x equals to 0, or alpha x alpha y plus alpha y alpha x equals to 0. So like that. So that is nothing but anti-commutation. So if AB minus BA is equals to 0, that is nothing but commutation. But if AB plus BC, sorry, if AB minus BA is equals to 0 means commutation, and AB plus BA equals to 0 means anti-commutation. So like that we have got some anti-commutation relations. So they anti-commute in pairs. We already have three well-known 2 by 2 matrices, sigma x, sigma y, sigma z, that is nothing but Polyspin matrices which satisfy above properties. So we also know about Polyspin matrices. So those matrices are nothing but this: sigma x 0 1 1 0, and sigma y 0 minus I 0, and sigma z 1 0 0 minus 1. So these are the Polyspin matrices. So these matrices satisfy these conditions also, that is their squares are unity and they anti-commute in pairs. So we also have sigma x sigma y plus sigma y sigma x equals to 0. So these matrices, they already satisfy this condition, and since a 2 by 2 matrix has 4 elements, there are 4 and only 4 independent 2 by 2 matrices. So these matrices, 2 by 2 matrices have 4 elements. So here if you see 0 1 1 0, so like that we are having 4 elements. So that one they are saying there are 4 and only 4 independent 2 by 2 matrices. These are, so we should have 4 independent 2 by 2 matrices because here 4 are there. There are 4 in number. These are 3 in number and this beta is another one. So 3 of these are sigma x, sigma y, sigma z. The only other linear independent matrix of these 3 is, so we should have linearly independent matrices. One matrix where one matrix not a linear combination of another 2 matrices like that. So here if we see another linearly independent matrices for these matrices, for these 3 matrices, another possible linearly independent matrix is this only, that is unity matrix 1 0 0 1 for these 2 by 2 matrices, which is a unit matrix and therefore commutes rather than anti-commutes with every sigma. But if we see sigma x into I is nothing but sigma x, and my so I into sigma x is again sigma x. So that is nothing but sigma x into I minus I into sigma x is equals to 0. So in both the cases, whether it is sigma x into I or I into sigma x, we are getting the same, that is sigma x. So it would satisfy commutation rule. Therefore it commutes rather than anti-commutes. That means this matrix, this another linearly independent matrix, this would commute with all of these 3 matrices, that is AB minus BA equals to 0. But what we needed here is anti-commutation. AB plus BA is equals to 0. But here it is commuting with every, hence cannot have fourth 2 by 2 matrix which satisfy both properties of Dirac matrices. So for these 3 matrices, the only linearly independent matrix is this. But this is not anti-commuting with them, but it is commuting with them. So it is not following the one of the important properties of Dirac matrices, that is anti-commutation rule. It is not following. Hence we cannot take these 4 as the Dirac's matrices. So we can't take this as alpha x, alpha y, alpha z, and this as beta. So a 2 by 2 matrix cannot be these Dirac matrices. So that is one important thing. So now we have to show that the Dirac matrices must be even dimensional. So we need to prove this. So let us see. Even dimensional means 2 by 2, 4 by 4, 6 by 6, 8 by 8, like that. We need to prove. So it must be an even number. Let us choose a representation in which beta is diagonal n by n matrix. So we need to consider beta matrix which has n rows and n columns. So here it is. N rows and columns means n number of principal diagonal elements. So this is a beta matrix. So here you can see only principal diagonal elements are present. It is b1, b2, b3, bi somewhere in the middle, and finally bn. So only principal diagonal elements will be present. Remaining all elements are 0. So this is the beta is diagonal matrix. And we already know that beta square is equals to 1 from the properties of Dirac's matrices. So if we do square of this matrix, so this matrix multiplied with the same matrix, this beta 1, beta I. So if we perform matrix multiplication, what we would get is, so here b1 square, bi square, bn square. So but beta square is equals to 1. 1 is nothing but unit matrix, that is 1, 0, 0, 0, 1 and so on 0. That means beta 1 square is equals to 1, beta 2 square is equals to 1, beta I square is equals to 1, beta n square is equals to 1, like that we used to get after squaring. If we based on this property and based on taking this beta as this, so beta into beta if we do, we would get beta b1 square, b2 square, like that. So on the right hand side we are having 1 1 1, that is identity matrix. So corresponding elements are equal, so you would have this bi square is equals to 1. That means nothing but sending this square to that side, bi is equals to plus or minus 1, where I is equals to 1, 2 and so on n. And also since beta square is equals to alpha k square equals to 1, where k is equals to x, y, z, determinant of alpha k or determinant of beta is not equal to 0. So here determinant of alpha k and determinant of beta is not equal to 0, they are saying. How they are saying this one is because alpha k square beta square would give us identity matrix, that is nothing but 1. That means lambda square is 1 if they are eigenvalues. That means we are having eigenvalues plus 1 or minus 1. So already we know that product of eigenvalues is equals to determinant of a matrix. For a given matrix, the product of its eigenvalues is equals to its determinant. So determinant of if so if lambda 1 and lambda 2 are the eigenvalues of matrix A, so the product of these eigenvalues must be equal to determinant of matrix A. So this is one of the very important formulas regarding eigenvalues. So hence as determinant would be equal to 0 if one of the eigenvalue is equals to 0. So when one of the eigenvalue is equals to 0, we would definitely we would have determinant equals to 0. But for beta and alpha case, we have already found out that eigenvalues of these matrices are plus 1 or minus 1. So minus 1 into minus 1 plus 1 we will get, or plus 1 into minus 1 we will get, but we won't get 0. So that is the thing here it is mentioned. So hence determinant of alpha k or determinant of beta cannot be equal to 0. So this implies that matrices alpha k k is x, y, z and beta has an inverse. So inverse of a matrix exists only when determinant is not equal to 0, because we know from the formula of a inverse is nothing but 1 by delta A into adjoint of A. That means adjoint of A of a matrix must be divided by its determinant. So if the determinant is 0, we can't divide it. Undetermined condition it is. So hence from this, as the determinant of alpha k and beta are not equal to 0, so they must have, alpha k and beta must have, definitely have inverse from the properties of matrices. Since beta anti-commutes with each component of alpha, we have, and also we have this kind of relationship, we have found it in Dirac's relativistic equation. So there alpha x beta plus beta alpha x equals to 0. Like in the same manner for alpha y, in the same manner for alpha z, we have this anti-commutation. That means beta anti-commutes with each component of alpha bar. So this relation may be expressed as, so this is the relation. Now what we have to do is we need to send this alpha k beta to that side. So on sending this term to that side, what we would get is beta alpha k is equals to here plus, on going to that side it would become minus. So minus alpha k beta. So next thing is what we need to do is multiplying with alpha k inverse on both sides in order to make here I, in order to get beta here. So alpha k inverse onto the left of both sides. So alpha k inverse, here also alpha k inverse. So alpha k inverse beta alpha k, here also minus alpha k inverse alpha k beta. But we already know a into a inverse is nothing but I, that is nothing but 1 here. So that I is represented as 1 in this manner. So this one would become I into beta, that is again we would get beta only. So this is the thing. So finally we would have alpha k inverse beta alpha k equals minus beta from this. Alpha k inverse beta alpha k, this term would become minus beta. So this is the thing we are getting. Now next thing is taking trace on both sides we get. So taking trace of the matrices on the both sides. So trace of this matrix and minus beta is there. That is nothing, trace of minus a is nothing but minus trace of a. So beta is a matrix and that one multiplied with minus 1 is nothing but minus beta. So that's simply we can take this minus 1 out and trace. Just find out the trace. That trace multiplied with minus is nothing but its own trace. Same. And next thing is another important property is trace of ABC. Here is equals to trace of CAB. So what is the meaning of this? First A is needs to be multiplied with B and then with C. And here first C needs to be multiplied with A and then with B. So whether whatever it is, first A, B multiplied or BC multiplied or CA multiplied. So trace finally for the product of these three matrices, trace of ABC is equals to trace of CAB. We could interchange the terms. So here we have sent this B to that side and C in the middle, CB. Again that C to that side and A to here. So CAB, like that. So here also the same thing happens. So trace of this matrix. Now what we need to do is send this alpha k to this side and beta to this side. So alpha k beta, and we already know that alpha k inverse into alpha k is nothing but I into beta is again beta. This is also minus trace of beta. So trace of beta is also minus trace of beta. Both of them are same terms. So now sending this trace B to that side, here it is minus, on going to that side plus trace B is nothing but 2 trace B equals to 0. So trace B is nothing but equal to 0. Has 2 goes to that side, 0 by 2 is 0. Trace B is equals to 0. Similarly, trace of alpha k in the same manner if we follow, we would get trace of alpha k matrix is as also equal to 0. So here finally what we are concluding here is trace of beta and trace of alpha k is equal to 0. So trace of this Dirac's matrices is equal to 0. So this equation shows that the trace of each of the matrices alpha k and beta must be 0. So that is the equation. So in matrix B, let R of the BI's are, so it is BI's. So this BI, these terms, diagonal terms, BI is nothing but these diagonal terms. So that one they are saying. So in matrix B, beta, let R of the BI's are plus 1 and rest of the BI's are minus 1. That means we are having totally n BI's. So out of these n BI's, they are saying R of the BI's are equal to 1. That means B1, B2, B3 and so on, B are equals to 1. And remaining BI's, that is R plus B of R plus 1, R plus 2, Bn is equals to minus 1. They are saying. So out of these n BI's, R of the BI's are plus 1. And the remaining BI's, that is SBI's are minus 1. And as we already know, plus 1 or minus 1, these are the eigenvalues. So we could include only the eigenvalues here. So that is bi is equals to plus 1 or minus 1. So out of them, so totally yeah, these n bi's are splitted into r1 bi's and s minus 1 bi's. So overall we would have r plus s is equals to n. And next thing is, but the condition that trace of beta equals to 0 requires that. So this condition requires trace of beta must be equals to 0. Trace of beta is nothing but sum of principal diagonal elements. That means sum of all these diagonal elements b1 plus b2 and so on, bi plus and so on plus bn, like that. So trace of all the elements, so here it is mentioned summation I equals 1 to n bi equals to 0. And we already know that as r of the bi's are 1, so r into 1, that is 1 plus 1 plus 1 plus 1 r times, and remaining rest of them are minus 1s, that is minus 1 plus minus 1 plus minus 1 plus of. So adding all these minus 1 for s times, so r into 1 plus s into minus 1, that is nothing but r minus s equals to 0. So from this we would have r equals to s. So now we need to substitute this in previous, that is r plus s is equals to n. So as r equals to s, r plus r, s is substituted with r plus r is nothing but 2r. So n is equal to 2r. So hence total n is nothing but total number of bi's. That means n is equals to 2r. That means even dimensional, that is 2 into 2, 2 into 3, 2 into 6. So we could have only even dimensional matrices. Thus Dirac's matrices alpha and beta can be even dimensional. So next, already we have checked for 2 by 2 matrices, that is Polyspin matrices. So they are not obeying Dirac's matrices conditions, so they cannot be. And next, therefore we cannot use 3 by 2 matrices. Next, after 2 by 2, 3 by 3, that also cannot be. And already we know that 1 by 1 matrix is nothing but just a numbers, so they can't be numbers also. So the next simplest case is 4 by 4 matrices. So now we have to look upon this 4 by 4 matrices. So as eigenvalues of all the 4 matrices are plus 1 minus 1, we have discussed it in the beginning itself. Let us arbitrarily choose beta as a matrix which is to be diagonal, and we arrange it rows and columns so that plus 1 eigenvalues are grouped together and minus 1 are grouped together in a matrices. So same as before. So plus 1, only plus 1 and minus 1 are the eigenvalues, and it has to be diagonal. And plus 1 eigenvalues are grouped together and minus 1 eigenvalues are grouped together. So only possible 4 by 4 such beta matrix is this. So I 0 0 minus I is nothing but 1 0 0 1, and 0 is nothing but null matrix, null 2 by 2 matrix 0 0 0 0, and here again 0 means nothing but null 2 by 2 matrix 0 0 0 0, and minus I is nothing but minus of I, that is minus of 1 0 0, minus of 1 0 0 1, that is minus 1, minus into 0 0, minus into 0 0, minus into 1, that is minus 1. So this is the beta matrix we could have. This is the compressed form of this matrix. Simply this matrix could be written as is from I 0 0 minus I, where I is a 2 by 2 identity matrix and 0 is a 2 by 2 null matrix. So this is the best possible beta matrix we could have based on these eigenvalue conditions, everything. And next, as beta anticommutes with each component of alpha we have. So we have discussed this earlier also. So alpha x beta plus beta alpha x is equals to 0. Same manner for alpha y, alpha z. So simply alpha k we could write. The JL element of which is, so here if we consider alpha k matrix multiplied with beta matrix and adding it to beta matrix multiplied with alpha k matrix, so in that element by element, corresponding elements if we see, so jth row and lth column element in that product. So actually we are having two products, this is one product and this is another product, and again we are adding those two products. So in general if we think, so jth row and lth column element of this would be alpha k jl and beta j plus beta l equals to 0. So y means here jth row lth column element would be beta L. So beta L we are having, and here jth row means beta J, like that. And alpha, that this element would be the same for both of them, alpha k j L. If we perform this product, we could have idea on this term, how we are getting this term. So finally we would have this term equals to 0 based on this condition if we do matrix multiplication like that. And here beta j beta L are two eigenvalues of beta which are arranged in accordance with equation 18. So beta j and beta L are eigenvalues of beta, as equation 18 means like this, plus 1 plus 1 minus 1 minus 1. So that one they are saying. And if beta j is equals to beta L, so if beta j is equals to beta L, if beta j is 1 and beta L is also 1, then we can't have 1 plus 1 is equals to 2. We can't have it equal to 0. And so alpha k j L is equals to 0. So y means this is of the form a plus b equals to 0. Either a equals to 0 or else b equals to 0. So when beta j is equals to beta L, we cannot have beta j this term equal to 0. So only possible thing is this term has to be equal to 0. So hence alpha k of jl equals to 0. Whereas if beta j and beta L have opposite signs. So if they are of opposite signs, if one is plus 1 and another one is minus 1, so both of them would add it together, we would get 0. So as this term is becoming 0, so this term need not be equal to 0. So hence need not be 0. Alpha k of jl need not be 0. So based on these conditions, the matrix form for alpha k may be expressed as. So based on these following condition, that is this condition especially, based on that condition, so what we would have is alpha k is equals to 0, alpha x1, alpha x2 0. This is the possible alpha k matrix where alpha x1 has n rows and m columns. So this matrix has n rows and m columns, and alpha x2 has m rows and columns, and this matrix has m rows and n columns. Means overall if we see, we would have m plus n rows and m plus n columns. So that is the thing. Since alpha x2 has m rows and n columns, so since the square of 19 is a unit matrix, so if we do square of this matrix, well, we have already seen alpha x square, alpha y square, beta square equals to 1. So that one they are saying, since the square of a matrix is unit matrix, we know that. So here what we need to do is, so if you multiply alpha k with alpha k, another alpha k, so this is another alpha k like this, 0, alpha 1 we consider, alpha 2, 0. So here if we multiply alpha k with alpha k, so what we would have is 0 into 0, 0 plus alpha x1 into alpha x2. So first element would be alpha x1 into alpha x2, but this must be equal to unity matrix. So first element in unit matrix is 1. So hence alpha x1 and alpha x2 equals 1. And if we see second term would be 0. 0 into alpha x1, 0. Alpha x1 into 0, 0. So here also alpha x2 into 0, 0. 0 into alpha x2, 0. 0 plus 0 as usual. And alpha x2 into alpha x1 plus 0 into 0. That is alpha x2 into alpha x1 again equal to 1. So from the product of these two matrices, we would get this form. So that means this must be equal to 1, as alpha k is equals to identity matrix. So that means nothing but this must be equal to identity matrix. 1 is nothing but identity matrix here. So you would have this this form, alpha x1 into alpha x2, alpha x2 into alpha x1 must be equal to I, that form. So unit matrix appearing on RHS as n rows and n columns, while the unit matrix has m rows and n columns. So they are saying about this product, and but no two matrices exist that satisfy 20A and 20B simultaneously if m is not equal to n. So if we see here, these both equations has to be satisfied simultaneously. So in order to make both the equations satisfy at the same time, it won't be possible if m is not equal to n. It would be possible only when m is equals to n. So that one they are saying. So if m is not equal to n, we cannot have these two equations satisfying at the same time. So hence, therefore we must have m is equals to n is equals to 2. So both of them must be equal and it must be equal to 2. So for that is for 4 by 4 matrices. This is the condition for 4 by 4 Dirac matrices. So it is apparent that alpha y and alpha z can be put in a form similar to 19 using Polyspin matrices sigma x, sigma y, sigma z, and choosing alpha x1 is also alpha x2 is equals to sigma x. Then so 19th form they are saying. So this is that form 0 sigma alpha x1 alpha x2 0. So here as we have found, we have considered this to be a 2 by 2 matrix, just like I 0 0 I. Here I 0 0 sorry 0 minus I. So this is a 2 by 2 identity matrix. This is also 2 by 2 matrix. So in the same manner, these are also 2 by 2 matrices. Overall we will get 4 by 4 matrices, and these matrices must be equal to spin matrices, Pauli spin matrices. That means alpha x1 is equal to sigma x. Sigma x is nothing but Pauli spin matrices. So like that one they are saying. So here it is given. So alpha x is equal to 0, alpha x1, alpha x2 0. So on the place of alpha x1, alpha x2, we are replacing it with sigma x Pauli spin matrix. So 0 sigma x 0. So 0 is nothing but null matrix 0 0 0, and sigma x is nothing but 0 1 1 0. Here also sigma x 0 1 1 0, and this is null matrix 0 0 0 0. So this is the 4 by 4 matrix, and in the similar manner alpha y is nothing but equal to 0 sigma y 0. 0 sigma y 0. Sigma y is nothing but 0 minus I 0. So 0 here, this 0 is nothing but null matrix 0 0 0. Alpha y is nothing but 0 minus I 0. And here also alpha y is nothing but 0 minus I 0, that Pauli spin matrix, and 0 is nothing but null matrix 0 0 0 0. So this is the best possible 4 by 4 Dirac matrices. In the similar manner, alpha z is nothing but 0 sigma z 0. So 0 is nothing but 0 2 by 2 null matrix, and sigma z is 1 0 0 minus I Pauli spin matrix. Here also the same Pauli spin matrix written in compressed form. So this is the compressed form of this matrix. So here we need to write 4 rows and 4 columns. These 4 rows and 4 columns. So simply we are just writing it as this form. We are using this form. So here all of them are 2 by 2 matrices. Every element is a 2 by 2 matrices. So for each matrix we would have 4 elements. So 4 into 4 16. Here also 4 rows 4 columns. 4 rows are 16 elements. Could be same. So already we have said about beta I 0 0 minus I 0 0 minus I. So that is the thing. So beta matrix, this is a beta matrix. These 4 by 4 matrices are evidently Hermitian, and in abbreviate form may be expressed as Hermitian means if the transpose conjugate of matrix is equal to the same matrix. That means if A is a matrix and this is the transpose conjugate of that matrix, so if they both of them are the same, that means for a matrix, if we find, let A be a matrix, if we do the transpose of that A matrix and again we find a conjugate of that matrix, so again if after doing transpose and after doing conjugation, if we get the same matrix A, the same matrix returns to its form, so that is nothing but Hermitian matrix. So these matrices, these Dirac's matrices are Hermitian, they are saying. So for example, if we do transpose of this matrix, so transpose of this matrix would be, this row would become this column. Here 0 0 0 1, Here also again we would get 0 0 0 1. Here 0 0 1 0. Here 0 0 1 0. It would be get converted to this form. Again 0 1 1 0. This row would be converted to this column 0 1 0 0, and this row would be converted to this column, like that. Rows would be converted into columns would be converted to rows. So again we would get the same matrix. And if conjugation, if you do conjugate of a is a, if a is a real, actually a plus ib, conjugation of a plus ib is a minus ib, but conjugation of a, if a is a real number, that is equals to a only. So conjugation of 1 is 1, conjugation of 1 is 1. So overall if we do transpose conjugate, we would get the same matrix, this matrix, that is alpha x is equals to alpha x transpose conjugate. Hence this is a Hermitian matrix. And in the similar fashion we would have alpha y is equals to alpha y transpose conjugate, alpha z is equals to alpha z transpose conjugate, and beta is equals to beta transpose conjugate. So because of that, all of them are called as Hermitian matrices. So in the similar manner, if we do for alpha y, if we do transpose, here we would get 0 0 minus I. Again if we do conjugate, minus I would convert to I. So again, so in mind we can say you get the same calculation, and in this row would convert it to this column. So 0 0 I 0 we would get. So conjugation of I is nothing but minus I. So again we would get the same in the similar fashion if we do for the same for these rows also, 0 minus I 0 0. So here like that, rows getting converted into columns, and the transpose conjugate, the transpose conjugate would become equal to this alpha y. So if we find transpose of this matrix, again conjugate if we find, we would get again the same matrix. Hence these matrices are Hermitian. So and in abbreviated form we may express it as, so abbreviated form in compact form. So beta is nothing but I 0 0 minus I. So 1 is nothing but I here, minus 1 is nothing but minus I. In the same manner alpha is nothing but 0 sigma sigma 0. That means it could be sigma x for alpha x, it could be sigma y for alpha y, and sigma z for alpha z. So this is the compressed form, where each element is a matrix with 2 rows and 2 columns. This element they are saying, so each of these elements is a matrix with 2 rows and 2 columns, just like I equals 1 0 0 1. I have discussed this. This is the elements, 1 2 3 4 elements are there, that is in compact form. So each element is matrix with 2 rows and 2 columns. So that is all about Dirac's matrices. So thank you.